Um, let's do another one. And this one you might recognize for sure as a problem that you can solve using dynamics and kinematics. So press pause, try to work through it using the work energy theorem, not the usual way, not the previous way that we've done it. And then press play when you want to go through it with me. So I'm going to look at a car. I'm going to say it's traveling to the right. And now I'm going to start to just, as these problems get a little more complicated, I'm going to be careful about talking about my initial event and my final event. So I'm going to say my initial event is when we begin to skid, and my final event is when we come to rest. The reason I'm choosing those two events is that I know what my speed is at this event, and I want to know what my speed is. No. I want to know what my position is at this event, and I do know what my speed is at this event because I'm coming to rest. Okay, so that's why I chose these two events. So in this case, how I've drawn it driving to the right, my free body diagram, the force that's going to make this object slow down would be kinetic friction, and that's going to be pointing to the left based on the fact that I drove my car going to the right. So the old way to solve it, again, would be to figure out the net force by figuring out how big the friction force is, set that equal to ma, solve for my acceleration, and then use kinematics with my v initial, with my acceleration, and with v final equals 0 to solve for delta x. Okay, that's the old way. The new way is going to be using the work energy theorem. So, again, this force is constant, so I do not need to perform an integral. I'm only, the object is moving in the x direction and my force is in that x direction, so I can use my very simple formula. I will have to choose the positive or negative. So in this case, as the force is acting to the left, the object will be moving to the right. So I'm going to say that friction does negative work, and actually kinetic friction always does negative work. So the work done by friction is going to be equal to negative of the force of friction times d. D will be the distance that we skid. This is what I'm trying to solve for. I'm trying to solve for d. What is the force of kinetic friction? That's always equal to mu sub k times my normal. Hopefully you can look at this problem and realize that your normal is equal to mg. Pretty straightforward. So that's how much work friction is doing, is given here. And because this is the only force that's doing work, that's also the net work done on my object. So there's my total work. Now I can plug that into my formula for my work energy theorem. And so here's the total amount of work I've done. And here is the change in my kinetic energy. Okay. Now I can plug in numbers. Since I come to rest at the end, V final is going to be 0. V initial is what I started with. That's 20 meters per second. Oh, and you'll notice that the mass cancels. In every term, there's an m, so I can cancel out the mass. Here I've plugged in mu sub k and g. D is my unknown variable, so then I can solve this expression for d. Now, in all the previous examples, I told you specifically that I wanted you to solve using the work energy theorem. And those problems, you can solve them also with kinematics and dynamics. It is possible. The problems that you have to use work energy for are problems that involve a spring. Okay, you have to use work energy for problems that involve a spring because the force that the spring is exerting is not constant, which means the acceleration of the object is not constant, and you cannot use kinematics when the acceleration of an object is not constant. Okay, so whenever there is a spring, you have to use work energy. So let's look at this problem, press pause, and try to work through it on your own, and then press play when you want to go through it with me. So I'm going to draw a picture. I have an object sliding in with some initial velocity, and it's going to hit this spring and compress it. I'm going to choose my events. My initial is right when the block reaches the spring, and my final is going to be when it comes to rest, and the spring is compressed 20 centimeters. Okay, why did I choose these? Well, I know what my velocity is here, and I know that the spring is not stretched or compressed here. And here, I know that my velocity is 0, and I know the distance that the object has moved going from here to here. Okay. So my free body diagram for the object, this is what's happening going from my initial event to my final event, and during that time, the spring is pushing the object to the left. So to figure out how much work is done, I want to look at how much work the spring force does on my object. This force is not constant. The more the spring gets compressed, the bigger this force will be. So because the force is not constant, I have to use the integration formula to calculate my work. So I'm going to look in the x direction, so I can write it as x initial and x final and a dx. And I know that my force, so I care about what my x initial and x final are. So let's call this position here x initial. That's when the spring is not compressed or stretched. That's the equilibrium position. And my x final will be at the x position of 0.2 meters. I want to do everything in meters, not centimeters. So this is the formula I'm going to integrate. The force of the spring is equal to negative kx. So I plug that in here. Here I've plugged in my limits. And then I just need to perform the integral. And that's pretty straightforward. Even though I don't know what k is, I'm just leaving k as an unknown value. That's what I'm trying to solve for. So this is how much work the spring does, and that's the only force that's doing work, so this is also the total work, or the net work done on my object. So here I've set the net work done on my object equal to my change in kinetic energy. Here I've plugged in, instead of net work, I put in the expression that I have, which is in terms of k. And here I say my final speed is 0, because that's what happens at this final event. And my initial speed was 5 meters per second. And then I can solve for k.